So this is a follow-up lecture to the Introduction to Analysis of Variance. In this video, I will just quickly review One Way ANOVA, or One Way Analysis of Variance. And then in the classroom, I will spend some time doing some actual problems. So this is more or less to sort of reinforce some of the ideas that I discussed in the earlier video on an introduction to analysis of variance. So analysis of variance really is a particular technique in statistics that involves an experimental design. And so this is a case where we have multiple levels of a factor that we're interested in, and we want to see what effect that particular factor will have. If we take a random sample of n individuals or n elements, and we randomly assign those n elements to the different factors, the sample sizes don't have to be the same for each of those. If that is the case, then we have a completely randomized design. And that's the case that we're going to talk about. Shortly after, I will do a separate presentation on two-way analysis of variance or randomized block design. Okay, so list a couple of terms that I think is be useful for us to familiarize ourselves with. One is a factor. A factor is a variable that the experimenter has selected for investigation. So for example, I talked about the amount of money spent on marketing. We could talk about the amount of nitrogen in fertilizer, so that if we were doing an agricultural experiment, we could be looking at the effects of different levels of nitrogen on the growth rates of plants and so forth. So that we call a treatment. A treatment is a level of a factor. So if we have, say, 3 different levels, then we have 3 different treatments, okay? And the experimental units are the objects of interest. In that case, it could be individuals if we are taking a random sample of people, or it could be some other thing that we're observing, such as, for example, automobiles. We could be looking at, say, sales at different stores. So it all depends on what we're collecting the data on, and those are the objects of interest, okay? And I've already mentioned that a completely randomized design is one in which the treatments are randomly assigned to the experimental units. In other words, we would take the sample and then randomly assign the people, if it is people involved, or the experimental units to the different levels of treatments, right? Or the different treatments. We use the word ANOVA as a shortened name for analysis of variance. And we essentially use ANOVA to test the equality of variances. Sorry, the equality of means, population means. And let me just get a nice thing. So in our null hypothesis, we'll typically state something like this, where the means are equal to each other. But in the alternate hypothesis, what we want to show is that somehow the factors or the different levels have different performance or have different effects. In that case, not all the means will be the same. And so you would have HA, not all the population means are equal. It could just be one that's different, which basically satisfies that condition that not all of them are the same, all right? Or not all of them are equal. And so that's typically what we're looking for. And so in terms of the hypotheses, as you can see them stated here, HO, all the means are the same versus they are not all the same. If we reject HO, then we support HA. If we cannot reject HO, and then we cannot support HA. It doesn't mean that we're proving that they're all the same. We're just not able to prove that they are different, all right? So if we ever reject HO, then we are concluding that at least there's one mean from the set of them that is different from the rest. There could be others, but then we're just simply saying that at least one of the means could be different. Now we need some assumptions, and those assumptions are very important because the technique that we will be using requires those assumptions. So one is that for each of the populations that the samples come from, that we say that they are normally distributed. So we have to assume that the populations are normally distributed. The second part is that we will also assume that each of these populations have the same variance. So in other words, if I have three populations, then sigma 1 squared is equal to sigma 2 squared is equal to sigma 3 squared is equal to sigma squared. In other words, they are all equal to a constant, all right? And that is important because the whole way in which we construct the analysis of variance is that we will try to estimate sigma squared with these two approaches, all right? Now, just kind of taking the conceptual approach, if we are able to somehow take the data that we get from our experiment and analyze the amount of variation and in the data that we collect, not only that, be able to break the data up in such a way that we could identify sources of variation within the data, then that actually helps us with our analysis. Let's see how that works. So we have a population, as you can see in this diagram, and that if HO is true, then there's just a single population and all the means came from the very same population. All right. In other words, the means are all the same. If the means are all the same and the standard deviation is the same, then clearly there's just a single distribution. And so the mean is mu, as you can see here, and then we're taking random samples from the population. And as we take those random samples, we observe the sample means. We see an X bar 2, X bar 1, X bar 3. All right? What will generally happen is that those sample means will tend to be relatively close to each other because they came from the same population. But what happens if we were to sample from different populations? Then there's a pretty good chance that the sample means that we observe will not be very close together. So you see, notice how those three here, those are different from the previous diagram that I just showed you. So what happens is that if HO is false, then we expect to see a fair amount of variation between the treatments. All right? Between the treatments, there's a lot more variation. So those values, X bar 3, X bar 1, X bar 2, should be much further apart than if we actually were looking at this situation where you could see them a lot closer, all right? Because they're coming from the same population. So we have to find a way to measure the variation among these, from the sample data, all right? So let's see what we have. It turns out that if we take the total variation and okay, for some reason my pen, maybe the battery is going dead, but if we take the total variation, and we'll have to find a way to measure that, we could break it down into two parts. We say that there's what we call between treatments variation. That means like from one treatment to the next. If we have 3 treatments or 4 treatments or whatever it is, then as we go from treatment to treatment, there's differences between the values. So in the case where the X bars came from the different populations, there is a variation across those different populations. So we call that the between treatments estimate of the population variance. So what it is that the population variance is sigma, and we want to estimate that. And the way we could try to estimate that, because the total variation in the data that we have is made up of 2 parts. One part we call between treatments, and the other one within treatments. Okay? Between and within. And to get a fairly good sense of that, what we're talking about is if we were to have, for example, factor level 1, let's take a different color, level 1, level 2, level 3, and we have a set of values for each sample from each population. I'll just put some arbitrary values right here. What happened is that if we go from sample to sample as we go across and we compare those, there's variation between the samples, but there's variation also within each sample. So these numbers, there's variation within them. There's variation within them. There's variation within them. So we could use the sort of within samples variation or within treatments variation to estimate sigma, or we could use between sample variation to estimate sigma as well. And then the question is that if the populations are the same, then what we should find is that the two estimates should be relatively close to each other. In other words, if we generate a mean square due to treatments, that's a variance. Remember, mean square is a variance. If that is the estimate that we get of sigma from the treatments, looking at the treatments, or we look at the mean square within treatments, MSW, some books call it MSE, mean squared error. If we look at that, if both of them are estimating sigma, then if HO is true, those two values should be close. But if HO is not true and the populations are different, then it means that sigma is not the same for all of them. So sigma could be the same, but the means are different. So what will tend to happen is that those two estimates will be further apart. Right? Those two estimates will be further apart. And in fact, if the means are not the same, what will tend to happen is that the mean square due to treatments will be much larger than the mean square within the treatments. And this is where we get this F distribution to help us out by saying F is the ratio of two variances. Remember we said that? So the mean square due to treatments versus the mean square within the treatments should be much greater than 1. All right? And in other words, this one should be bigger. Why? Because we expect more variation across the treatments if HO is false. So by getting an F value that is much larger than 1 supports HA. And so in essence, that's what we're looking for. All right? So how then do we calculate the values that we want? So the mean square for the treatments is made up of two parts. And remember what a variance is. A variance is a mean square divided by degrees of freedom. So for example, when we had, let me just go back for a second, and I will introduce a clean page. So for example, when we found S squared was SSX over n minus 1. So basically a sum of squares over what is the degrees of freedom. So that's essentially what that is. Sum of squares divided by the degrees of freedom is sample variance in this case. So we could see that, right? So if we go here, this numerator is a sum of squares, but it's a sum of the squares associated with the treatments. And the way in which we do that is we say, let us take the overall mean of all of the data. Let's take the overall average, all right? If we take the overall average, how far are the sample averages from that overall average? And what then we do is that when we multiply it by the sample size and add it all together, we will get the sum of the squares as a result of the treatments, SST. That's the way to represent that. And then if we divide it by the degrees of freedom, K minus 1, because they're K treatments, so K minus 1 is our degrees of freedom, we actually get a variance, which we can refer to as the mean square due to treatments. All right, so remember, mean square is a variance. So that is the between treatments estimate of the population variance, MSTR. So the denominator, as we can see here, the denominator is the degrees of freedom, and the numerator is called the sum of squares due to treatments. All right. So that's how we get the between treatments estimate of the population variance. Now let's look at the, let's look at the within treatments. So what we do now is that with each sample, we will actually generate the sum of squares. So we will take the sum of squares for sample 1, if there are 3 populations, plus the sum of squares for sample 2, plus the sum of squares for sample 3. When we add all of that, so that will give us the sum of squares for within treatments. Well, it turns out that SS1, SS2, SS3 is actually this numerator right here. So notice what we're doing. We take in nj minus 1 and multiplying it by sj squared. J basically representing the treatment, the different samples. Let's see why that makes sense. All right? Let's see why that makes sense. So take a look at this. We said, let's go with my S. Let's go with a different color, sorry. I think we could see this. So think about a sample, standard deviation, no, variance, sorry. Not standard deviation, but variance. Let's take out the subscript for now. So S squared we know is basically SSX, right, over n minus 1. Sum of squares over n minus 1. And remember how we get S. S is just the square root of SSX over n minus 1. But we have a formula for SSX, which we said was sum of xi minus x bar squared, right? That's the sum of squares, but I gave you a shortcut formula. I'm going to keep it at this level for now because it will show you what we mean on the other side. So now, if I actually cross multiply this, what do I get? I will get s squared times n minus 1 is equal to a sum of squares. I'm sure you'll agree with me on that, right? So if that is the case, let's take a look at what, so s squared times n minus 1, or if I put it n minus 1 times s squared is the same thing. So if I have different samples, and my samples for each treatment, nj, so then I could call this s squared, sorry, j. I put the square on the bottom, which is a mistake. So to make it nice and neat, so you could see how this term right here would be the sum of squares associated with treatment J, right? That's what that is. This would give us the sum of squares associated with treatment J. So let's go back now and see what we have. So if you look at this, we have nj minus 1. So nj minus 1 times sj squared is the sum of squares associated with treatment J. So if I want ss1 plus ss2 plus ss3, essentially, what I should be then doing is to take n1 minus 1 times s1 plus n2 minus 1 times s2, so that's s squared, right? Plus n3 minus 1 times s squared 3. So that's for 3 samples, if I have 3 levels of treatments. So basically, by adding all of those up will give me the sum of squares from treatment 1, sum of squares from treatment 2, sum of squares from treatment 3. If I add all of those up, essentially I'm getting sum of squares due to within treatments. So MSW, right? Sum of squares within treatments. Let me see how we refer to it here. I just got to make sure that is MSE. So it's actually called sum of MSE, sum of squared errors, but a popular term that is also used is the sum of squares due to treatments. I prefer MSW because it talks about within the samples, but anyway, our textbook uses MSE, so as long as we know that it's the same thing. So going back to my diagram right here, just to be consistent, I will refer to this as MSE. So the mean squared error is the sum of squares for each of the samples, and then SS1 plus SS2 plus SS3. But then we have to remember that a mean square, which is a variance, is the sum of squares divided by the degrees of freedom. Each sample has degrees of freedom n1, n1 minus 1, or nj minus 1, that is. So n1 minus 1, n2 minus 1, and 3 minus 1. So these would be the 3 different degrees of freedom. If we add them all up together, what we will find is that it becomes n minus k. Here's why. Because the sample sample for 1, treatment 1, plus the sample for treatment 2, the sample for treatment 3, all adds up to the overall sample size. But look at this. We have 3 treatments. So 1, 2, 3. That's the k treatments right there. And so it's n minus k. So MSE, if we look at the formula, we will realize that it is the sum of squares within the treatments, which is this term right here, divided by nt, which is the total sample size, minus k. That is the number of treatments, and that is the degrees of freedom. Okay? And that gives us the mean squared error, or the mean square within the samples that we have. Okay. So now we have the 2 estimates of the population variance. One is between treatments, the other one is within treatments. And so now we compare those 2. Now you will recall that I mentioned to you that an F distribution is the ratio of 2 variances. All right? And there's a numerator variance and a denominator variance. So in the case of the numerator variance, which is between squares. So here's how we will actually measure the strength of our evidence, is that we will generate the F distribution from using the mean square within between treatments, MSTR, divided by the mean square within treatments. So that's the ratio of the 2 variances, and that's an F distribution. For the MSTR, the degrees of freedom was k minus 1. For MSE, is nt minus k. All right? And so we have the numerator degrees of freedom and the denominator degrees of freedom. So now, we now have what we call a test statistic for doing an analysis of variance. And what we're looking for, remember we said, if the HO is true, then the 2 estimates of sigma should be close. But if HO is not true, the 2 estimates will not be close, and typically MSTR will be larger. Why? Because the sample means that are generated from these 3 different populations are going to be further apart. So therefore there'll be more variation among those sample means compared to within the samples. And so as a result, we're looking for larger values larger than 1. Okay? So if the means of the k populations are not equal, the value of MSTR over MSE will be inflated because MSTR overestimates sigma. All right? Hence, we will reject HO if the resulting value appears to be too large to have been selected from a random sample, right? That reflects H0, where the means are all the same. And so this is what our decision rule will sort of look like. This is the F distribution is skewed, kind of like the chi-square distribution, but perhaps not with a long tail like the chi-square. And we could see here's our rejection region where alpha, we would reject the null hypothesis, and we have the ratio of the 2 variances. With our degrees of freedom, we could actually find the critical value over here. So F alpha, critical value, but with the 2 different degrees of freedom, one which is k minus 1, and the other one which is nt minus k. All right? So that would be how we would find that. One of the nice things we could do is that we could create what we call an ANOVA table to summarize all of our information. And the ANOVA table looks something like this. So here is sources of variation, because we're taking the overall variation and breaking it up into two parts. The two parts are variation due to treatments and the variation due to the error. In other words, what we cannot explain. And there's total variation. So we call sum of squares SSTR, so that's our next heading. The sum of squares due to the treatments, sum of squares due to the error. And if we add them up together, we get the total sum of squares. The other thing is that we have degrees of freedom, which is k minus 1 for treatments, because there are 3 treatments, or k treatments, so k minus 1. And then the degrees of freedom for the error will be nt minus k. Because remember, what we're doing is we're adding up n minus 1 and nj minus 1 for each of the treatments. So it becomes n minus k. If we divide the sum of squares by the degrees of freedom, we will get the mean square, which essentially is a variance. Remember, sum of squares over degrees of freedom. And so now we have MSTR, which is the mean square due to treatments. It will be SSTR over its degrees of freedom. And then we have MSE, which is sum of squares due to the errors divided by the degrees of freedom. So now we have the two variances. If we take the ratio of them in this F statistic, then we could actually go ahead and compute an observed F value and compare it to our critical value. We could also compute the P value associated with this ratio, and then compare it to alpha when we need to. Sometimes we need the total sum of squares. The total sum of squares is this formula right here, which, as we said, it was broken up into sum of squares due to treatments and sum of squares due to the error. One of the nice things about this is that this formula, we already, even though it looks strange, we already know what it is. The total sum of squares is basically obtained by pretending that all of the data is a single sample. So if we took all of the values that we had, in other words, if we took, let's see, N1 plus N2 plus Nk, if we add them all up, we just get a big sample size, Nt. You call it N total. So if you have all of these these samples, and you make those samples, and you pull them all together into one big sample, then we have N. So how do we find the sum of squares for one sample? Remember that S squared is SSX over N minus 1. But this sum of squares due to X, we have a formula for it. Xi squared sum of Xi all squared over N. That is, this term right here is our SSX. So we already know how to do this from our standard deviation calculation. So if we need to find the total sum of squares, we can do it very easily by treating all of the samples as a single sample, all right? And then calculating this value. I think it's a lot easier for us to appreciate it now if we begin to look at an example. So let's just very quickly summarize what the hypothesis test would look like. It would be H0, mu1 is equal to mu2 is equal to mu3 equal to mu k. And not all the population means are the same. Test statistic, F is equal to the ratio of the mean square due to treatments divided by the mean square due to the error. That's step 2. Then, of course, we determine our rejection rule. If the p-value is less than alpha, we reject null hypothesis. Or we reject HO if the observed F value is greater than our critical value, F alpha. All right? And then we must do our analysis and come to our conclusion. So those first 3 steps are very important. Here's an example. Let's go over that very quickly. So we have to kind of keep in mind the formulas that we have. We have Autoshine Inc. is considering marketing a long-lasting car wax. 3 different waxes, type 1, type 2, type 3. So you see, these are the factor levels. Whatever is in the wax, whatever the active ingredient is different for the different types of car waxes. Car wax is used to shine your car. When you wash it, you want to polish your car and make it look really nice. So in order to test the durability of these waxes, 5 new cars were waxed with type 1, 5 with type 2, and 5 with type 3. So they made this test or experiment balanced. That means that they use the same sample size in each of them, but with a randomized design, you do not have to have all the sample sizes the same. So the data looks like this. So then basically what you collected was the number of times each car can go for a car wash before the wax actually disappeared. All right? And so factor is the car wax. Treatments, we have 3 treatments for the car wax. Experimental units, the cars. The response variable, how many car washes that we could get. And we have data that looks like this. So 5 observations in each sample. And here's the number of car washes for each. And we want to know if the average is the same or there's a difference between them. Now, if you look at the sample means, look at this, 29, 30. So we could actually set this up in Excel very nicely. Find the sample mean. So this would be X bar 1. This would be X bar 2, X bar 3. And we could also find the sample variance, which is S1 squared, S2 squared, S3 squared. Now remember, we're going to use that when we want to calculate MSE, all right? Because to calculate MSE, we need NJ minus 1 times Sj squared. Sj squared is the sample variance for basically for sample J or treatment J. So we could set this up very nice and very easily in Excel. So here are hypotheses. The means are the same versus they're not all the same. And we define what the means are. Mu1 is the number of car washes for type wax 1, mu2 for wax 2, mu3 for wax 3. Fairly straightforward. Now, in terms of getting a test statistic, we know what the test statistic is already, which is MSTR divided by MSE. And then now we must find a decision rule. Now, we weren't given a decision rule yet, but we'll come to it very shortly. So let's actually find the mean square between treatments. And if you recall, that would be MSTR. The formula for that was essentially we multiplied the mean for treatment J minus the overall average squared. So we square that difference and multiply by that by the sample size, and then we add them all up together. So that's what's being done here. So as you can see, we take the sample means, if we divide by 3, we get the grand mean, and then for each one of those, we would look SSTR. We would take the sample size, which is NJ. This is the sample mean, and the overall sample which is 29.8. Then we do the same sample size for treatment 2. Here's the mean for treatment 2, and here's X double bar. Sample size for treatment 3, sample mean for treatment 3, X double bar. So when we do this now, we could find MSTR, okay? Which we know is MSTR is SSTR divided by K minus 1. So here we have it right here, and we will now have MSTR. If we repeat this now for the mean squared error, remember we said was essentially NJ minus 1 times SJ squared. So if you look, you'll see that this is 5 minus 1, which is 4, and we already have the sample variances. 4, sample variance for treatment number 2. NJ minus 1, 5 minus 1 is 4, and the sample treatment and the sample variance for treatment number 3. When we add it all up together, we get 33.2. And now we're going to divide that by n minus k, where n is 3 5s of 15 minus 3 treatments gives you 12. When we do the division, we have 2.77. So now look at the ratio of MST. If we compare MSTR to MSE, those are not very different. So therefore, we are not going to get a very large F value. So if we're going to do the p-value approach, then we will reject if the p-value is less than 5%, if we use 5%. Or critical value approach, we will basically need an F alpha, degrees of freedom 1, degrees of freedom 2. In our problem right here, it would be F 0.05 and K minus 1, which is 3 minus 1, which is 2. Right? And then NT minus K, which was 15 minus 3, which is 12. So that is our critical value right there, F05 to 12. And if we use the F distribution, then we will find its critical value at 3.89. With 3.89, if we compare the fact that we're not going to get a value that is greater than 1 or much greater than 1. If you look here, F is equal to MSTR over MSE, 260 over 2.77, and therefore we have less than 1. So clearly the p-value is greater than 10% if we look it up, and this is clearly not larger than 3.89, right? So therefore we would fail to reject HO. There is insufficient evidence to conclude that the mean number of waxes for the 3 wax types are not all the same, right? Or that there is a difference between them. So this could be a company that actually spent some money trying to develop these 3 different waxes, only to find out in the end there's really not a big difference between them. So all of that investment in trying to create a better wax, really and truly did not really help. So here's how we would summarize this information in a data table. We could see for our problem, we have the sum of squares for treatments is 5.2, 33.2 for error. Degrees of freedom was 2, was 12. And then when we divide the sum of squares by the degrees of freedom, we get a mean squares. 2.6 and 2.77. When we take the ratio of those two, we got 0.939, which has a p-value of 0.42, which is very high. And we could also add to that our F critical to the table, if we want to do that. And that way we could see very quickly that 0.939 is not larger than 3.89. So therefore we'd fail to reject HO. And that's essentially it. All right. Here's another question that was also done in terms of another example. This one has to do with 5 managers from 3 plants were taken, and the number of hours worked by each manager in the previous week is shown on the next table. So we take a random sample of managers from these 3 locations, 3 plants. A plant could be in any 3 cities that you want. We could take one in Shenzhen, a plant in Guangzhou, a plant in Zhongshan, and we're actually looking at whether the managers work a different number of hours. So we take a random sample from each of them. So if you look at this data, we have 5 of each. So that's also a balanced design, but it's not a randomized block design. We have the sample means for each of those. And if we average those values, we'll get the grand mean. We take the sample variances as well. Okay. Here's our hypotheses that essentially mu represents the mean number of hours worked by the managers. And so mu1 for plant 1, mu2 for plant 2, mu3 for plant 3. And we specify the significance level, 5%, and compute the value of the test statistic. So if we do this, We have X double bar, which is the grand mean, and we just simply average the three means from the treatments, and we will get that. So it's 60 in this case. Then we take the sum of squares due to treatments, and remember the formula was that we will take each mean and subtract the grand mean from it, square it, and multiply by the sample size. And we do that for the three of them. We get 490 as SSTR. So MSTR is 490 divided by K minus 1, 3 minus 1, 245. Now we're going to find MSE. To find MSE, we will need SSE, which is Nj minus 1 times the variance. So if you look, we have 4 times 26, 4 times 26, and so on. So 308. And then MSE is equal to 308 divided by 12, 25.67. So if I go back, if we look at that, we see one estimated at 25.67, whereas the other one estimated population variance at 245. So here are the two estimates right there. One is estimating population variance at 245. One is estimating it at 25.67. So clearly there's a problem. And the only way that could be explained is that essentially those samples did not come from the same population mean. Population with the mean. It came from different populations. All right? And so therefore, we will conclude that there is enough evidence to reject HL. We could also find the p-value. So here we go. We could summarize our data as we see here. And here's our F value. The critical value, if we're using the critical value approach, is still the same. F critical is 3.89. As you can see, 9.55 is bigger, and the p-value is less than 5%. It's less than alpha. So therefore, we reject the null hypothesis and conclude we have sufficient evidence that the managers work different. In other words, they don't all work the same average number of hours. Right? So critical value approach, 3.89, and we could see that we're comparing the 3.89 right here. So that's how we would essentially do this problem. And we would be able to conclude a one-way analysis of variance, all right? So doing it in Excel, it would be actually quite the best way because of the sheer number of calculations. We wouldn't want you to have to do this by hand. So there you go. That is one-way analysis of variance.